In this lecture, we're going to begin by looking at I/O. So far, you've been using some predefined output tasks such as $write and $display, and we have another one we want to look at called $strobe. And just for a refresher, the $display looks like the write, but it appends a new line. However, the $strobe is like the $display, but the display occurs at the end of the current time step, and it ignores transient values and displays only the final stable value. So in other words, when we've done all of our assignments, everything is completed calculation-wise for the current time step, then the $strobe is going to execute just before we go to the next time step, before we update the simulation time. Let's take a look at format specifiers, and some of them we've been using already, like %b for binary or %o for octal, etc. There's also a thing you can put in here. You can put a number just before the b, the o, the d, or the h, such as you could put a 0, and if you do that, it'll display the minimum field width. If you don't put the 0 in front of it, then, or some other number, it's going to display a different field width, and it'll take, if you put no number in front of it, it'll always take the maximum required width. So we also have %f for real, %t for time, %c for character, and %s for string. If you want to have special characters, you can have a new line using this notation, or a tab, and you can even print out a quote and a backslash as long as you put a backslash in front of those characters. If you want to print out the % sign, then you have to put the %. Also, you can print out octal ASCII values by using this notation. You can also use a special %m that will print out the path name to the module. There's no argument needed in your string, but if you put this in the string, it'll actually print out the path to the module of the statement that's being executed. We'll take a look at this in a second. Also, if you're printing out some digit and all of the bits corresponding to a digit are a 1-tick BX, then you'll get an X displayed. So say you're printing out some 4-tick hex value, but some of the bits were, or all of the bits were 1-tick BX, then the display will be a lowercase x. However, if some of those bits corresponding to the digit are not a 1-tick BX, then a capital X will be displayed. So in other words, just some of the bits, but not all. And similar for a Z. So if all of the bits corresponding to a digit are a 1-tick BZ, you get a lowercase z displayed. Otherwise, you get an uppercase Z. So the argument is a sequence of a formatted string and data to be formatted. Here we're using the write statement, and there's our octal value, which could ring the bell on a terminal. And then we have that %m here, and that'll print out the actual module that this write statement is executing in. Okay, notice there's no argument over here for it. This argument here, error count, goes with this %0d, and this will print out the minimum field width. So one of the things I want you to try is look at the difference between printing things with %0d or b or whatever, and those statements that don't use the 0 in front of it. And also try putting some other numbers in there and see what happens. The %c format specifier interprets the argument as an 8-bit ASCII value. So here we've done a write with a %c and a %0d, and we've given both arguments the same value here of 65. But in this case, this 65, it'll print uppercase A, because that's the value for an uppercase A, and we've told it we're going to print a character. And then for the %0d, we just print the actual 65 value. Now for the %s format specifier, it interprets the argument as a concatenated 8-bit ASCII value. So here we have %s and then %0d. Now this, with the curly brackets, that's our concatenation operator, and we've concatenated two 8-bit values together. That's what this says. And this %s then prints that in terms of characters, basically. So you get the uppercase A and uppercase B, and then this one just prints as 67 because we told it that it was just a decimal value we're printing. Predefined formatted output task to monitor registers and wires is called the $monitor task, and this is the syntax for it. And basically you have a formatted output. So here we're using it in this example. Again, we're using the %m. It'll print out the module. Notice there's no argument for that. %t will use this argument, $time, and the %b will then print this state. So when does this actually execute? Let's look at what the equivalent is of this monitor statement. It's equivalent to writing it always at state. The state is this one here that we're monitoring. And then we have strobe %m, same as this one up here, at %t, and %b, and then time and state. So notice this is whenever state changes value, not necessarily a pause edge or a negative. This is just any change at all. Okay, and it's the same as using the strobe statement. And remember, the strobe doesn't print when it's executed. It actually waits until the end of the current time step when everything, all the calculations have finished and they're done, everything's stable, just before it increments the time. The monitor format is displayed whenever one or more monitored wire or register changes, not when the statement is executed. That's what we're talking about here, the change, and not when the statement's executed because it's a strobe. You can only have one active monitor, so the last $monitor statement executed is the one that's active. The thing to remember about using this $monitor task is it'll slow down your simulation quite a bit, but you can turn it on and off by using these statements. Now let's talk about other types of output for file output. We have the $F tasks, and these are like $F write, just like the $write for display, strobe, and monitor, except all of them are to file output. So the first argument for this file output is an integer file handle, and so you have to declare some integer and then some value, some value for this FP, and this FP is what you will need to use for the file handle, or whatever you happen to call it. And so here's the syntax: $F write, FP, and then whatever you would normally do a write. Same thing for display. So how do we get the file handle? Well, we use the file open task, and when you do a file open, it's opened in the overwrite mode, and it initializes an integer file handle, and it returns 0 if the operation failed, and there's a maximum of 31 open files that you can have. And this is the format here, F open and then the file name. So here's how we get our file handle, and we have integer FP equals F open. We check to see if it returned a 0. If it is, we print out there was a problem. So that's fairly similar to C. There's also a $F close, in which case you feed it the file handle of the file that you have open, and once you close it, the file handle is no longer valid. So here's the same code again, and we've added a $F close with the file handle that we were using previously. However, on file input, it's a lot weaker than file output. We can only read files for binary or hexadecimal numbers into memory, and the file format is predefined. Simulation does not stop if a warning or error message occurs during memory loading. So let's take a look at this now in just a moment. Also, in the file format, you have blank separations between the numbers, and you cannot use a size or a base specification, only digits. And the numbers have to be either all binary or all hexadecimal. They're truncated or zero extended as required, and they can contain X and Z. We also have what's called address relocation, and this is the syntax for it. You put an @ sign and then a hexadecimal address. You can also use comments, and these should be familiar, or this format. So here's an example. Here's a file that we're going to read in, and notice we have, in this case, binary values, a binary value here, an 8-bit binary value here, separated with a space, and then another 8-bit binary value. That's okay. Here's a line comment. That's okay. This line here, though, is invalid. You cannot use a size specifier. Okay? So it is a bit limited in that respect. Here's another block type comment. Here's where we've changed the address to be FF. So this next value after this is going to be loaded at address FF. And then here we've changed the address to 0. So the next value right here will be loaded into address 0. And then this is invalid. Okay, so we were doing binary. We can't mix and match hex and binary. So this is a no-no. Here we have another file. Now this one has hexadecimal values. So here we have a hexadecimal value separated with blank space. Another hexadecimal value, our comments. Again, you can't use the size specifier. Here we've changed the address to FF, so this loads into address FF, and we've changed it to 0, so that loads into, so the BC loads into address 0. And here we've put an 8-bit binary value, but because we're in hex mode here, it's just going to truncate and use these lower two, thinking that this is the hex value of 10. So it'll just truncate it. So you have to be very careful with this file input. So how do we pull this file input in? Well, there's two tasks, predefined tasks, called readmemb and readmemh. Okay, so one's for reading binary values in, the other's for reading the hexadecimal values in. So it's going to expect either binary or hexadecimal depending on which one of these you use. So now you have the format here. The syntax is you have a file name, and you have the memory of where you're going to put all these values, and then optionally you can have a start, okay, and then optionally you can have an end. Okay, so if you don't specify the start, it's going to start at the left-hand address if you don't specify it, and I'll show you what we mean by that. And the file must, if you put the end, then the file must contain the exact number of values if the address is specified. Here we have an example. We've set up a chunk of memory called prom. Now it's 8 bits wide and it's 8 deep. Okay, and the start here is 7 and the end is 0 for this particular memory. But now we're going to actually read by doing a readmemb. So we're told that we're going to read binary values in, and we're going to read it from this file name, and this is where we're going to put it in prom, this memory here. So we start off, let's say all of our contents of our memory is all set to hex XX. Okay, it's not initialized. So we start off and we read this first value in. Well, this first value, that's an 8.6. Okay, so it's going to start, because we didn't specify start, it's going to start at this one. Okay, not 0, but it's going to start right here. Okay, so where's it going to go? It's going to go into prom location 7. So there's our 8.6. Okay, so where's the next one go? Well, the next one would go to the next address, so the F4 that we have here would go into address 6, because that's the order that we've put these in for this particular memory. So this order here plays an important part as to where things get placed when you read out of the file. Now we've changed the address to 0 and we read in this value. Well, now you notice we did put an 8-bit value, so it's going to 0 fill the upper part. So this will be a 1F, and this would then go at address 0 right here. Okay, now we've changed the address back to 5. And so this value of 5A is going to go at address 5, of course. And then the next one, well, according to the order here, it would go in address 4 would be the next one, so we'd see an FF go into this one. Now let's take a look at the same example, except this time we're changing the start and the end to go from 0 to 7. So we're going to do a binary read type file here of problem MB. Here's our problem MB file. And the first value, 86, will now go in address 0 because that's our start. The next value of F4 will go in address 1 because of our order. Then we've changed back to 0, and we've said to put in the 1F there, so we've overwritten our previous value we put in there. Now we change to address 5, we put in our 5A, so we get our 5A. Then the next value, because of the order, is going to go in address 6, so the FF will then go in address 6. Now let's look at this same example again with the same start and end order and values, but this time we're telling it in the readmemb statement that we're going to start at 2. So our first value of 86 goes into address 2. Then our next value, because of the order here of the prom, will be address 3, where we put our F4. Then we change back to 0 and put in our 1F. Then we change to 5, put in our 5A. And then the next address, of course, would be 6, and that's where the FF goes. Now let's look at it one more time, except this time we're going to have a start of 2 and an end of 6. Okay, our same prom memory goes from 0 to 7. So here's our file. We have an 8, 6, and that will start going in at location 2. And that's what we have here. Then location 3 would be our F4. And then we said change to 0, but this is an error because we've run out of this range. Okay, once you specify the range here, you have to stay in that range. So that's an error. Now what I'd like you to do, in addition to your lab, is when you have this error, what's going to happen with the rest of this? Okay, I want you to actually play with it and see. I'm not going to tell you. I want you to go try it out. Does it actually continue to put stuff in memory, or does it stop? In Lab 6.1, I want you to learn the difference between the $right, the $monitor, and the $strobe statements, and learn how strings can be passed around, and learn how to initialize a design from a memory image file like we were doing. Let's take a look at some more advanced statements now. And the first are named blocks. So you've noticed before that you can have a begin and an end block where you put one or more statements between the beginning and the end. You can also optionally name that block, okay, by putting a colon and then a name. So here we have an example. Here we have a begin-end block for this always statement, and we've named it sample. So that's how you can name a block. Named blocks, this is one of the uses for a named block. Named blocks can contain local register declarations, and those local declarations may hide a more global declaration. Okay, we're going to look at how that's done. So the guideline here is to use local declarations for registers used solely within a block, and reserve global declarations for registers used by different blocks. So here we have an example. We have two blocks, and we have this always block here with this begin end block, and we have another always block with this begin end. Now let's say both of those blocks you wanted to make a for loop, and you like using the integer I, and so you did this one using I and you did this one using I. Well, both of these i's are actually referring to this integer I here. So that's not really what you want to do, because both of these always are executing in parallel. You don't want things messing up. So the thing to do is you can name them, okay, and then put your integer I within that block, and then this integer I is local to this block. Same thing with this one. Okay, so now each block has its own register I. Inner declarations will hide outer declarations. So let's look at how that's done. So here we've said that we have an integer I and j. Now these are global to this initial block here, and then also this initial block. So here in this initial block we have a begin-end block that we've named A, and we've said we have a local integer I. So now when we do a write and we use I in that write statement, it's referring to this local integer I. And this j then, because there's no local j, refers to this global j up here. Okay, similar, now within this block called A, we have another block here that we've called B, and it's declared some local integer I and j, so that when we use a write within this block, it's going to use these local, these right here will be these local I and j. And this write, though, is within the block A, not within block B, so this would use this I here, and this j would use this global j here. Similarly, this initial block would then be using the global I and j, okay, because it's not part of this block, or this initial block. So these are the I and j. So that's one of the uses for a named block. You can also disable named blocks by using the disable statement. The disable statement aborts the execution of a block and forces execution to continue after the end of our begin end. And a block can be disabled internally or from another block. Okay, that implies that disabled block is which implies that currently disabled block is currently waiting. So it's one way that you can model reset. There's other uses for it too we're going to look at. Here's the syntax: disable and then the block name. So here we have a block called begin end block called ME, and we've used a forever statement. Okay, so this is going to go forever unless we do something such as the disable. So here we've said if we have ACK equal to 1, we disable ME, which forces the execution to go down to right after this end of the begin end block. So when this disable occurs, then it executes down here at the write statement next. Here's another example. Here we have a for loop, and we've named this begin end block here next, and then we do stuff in here, and we said that if this certain condition happens, then disable next. Okay, well that means that you go to the end of this begin end block. So the next thing to execute after the end statement is actually the for. Okay, so execution jumps right here, which then takes you to the next loop iteration. Okay, it doesn't abort this for loop. Okay, it just aborts the begin end block that you've declared here. So be careful with that. Okay, the for loop is not disabled since it's not in the begin end block. Remember, you have a for statement, and then you have either a begin end compound, a compound statement using the begin end, which is the same as a single statement, but that doesn't abort the for. Here's another example. we have this block called right cycle, and we come down through here and we say at neg edge of AS, or we're waiting for that, address equals this, then at neg edge of DS, where we're waiting for this neg edge of DS, then we continue writing these statements. Goes down and it loops doing this forever. Okay, so we always keep looping here in this always block. So now we have another block though that's doing something different, and it says wait for reset equal to 0, and when that happens it says disable right cycle, so it'll actually disable this block. So if we're sitting here waiting for the neg edge of AS, then it's going to jump down here. If we should be waiting for the neg edge of DS, then it would jump down here because of the disable. And so the reset block disables the other block regardless of its current state. So no matter where it is in here, it's going to disable it. So this is a case where you can disable another block from, or disable this block from this block, a different block. Now let's talk about a fork join statement. Let's say that you have some code that some things you want done sequentially and other things you want done in parallel. So here we have, I'm representing horizontally by being sequential, things done sequentially, and the vertical scale here by things being done in parallel. So here I have a block, and I've said this just represents one or more statements here. We're just calling them A, statements A, and when those statements are done, then I'm going to set a flag called done. Okay. Now, after this block executes, I want these two blocks to execute in parallel, and then after both of these have finished, I want this to be executed. Okay, so this is our sequential order, but these two here I want to be done in parallel. So what we've done here is I said, okay, in this block we're going to wait until done 1, and in this block it waits till done 1 is true. So both of these are sitting waiting for this block to set this flag, and then both of these will execute in parallel, and then for each of these blocks we've set a done 2 and a done 3. Okay, so this block is going to wait until both done 2 and done 3 are done before it executes some statements. We'll call those statements D. So here we have a case of sequentially we want A, then we want to do B and C in parallel. When both of those are done, then we want to do our statements D. So this sequencing has been explicitly modeled, and we're going to find an easier way to actually do this using the fork join. So the fork join statement, here's the syntax. Let's look at the syntax. You have fork join, and then you have statements in here. So it executes statements in parallel in the middle of sequential statements. So here you may, let's say you had a dozen sequential statements. All of those would be executing in parallel in this fork join block. So the sequential execution is suspended at the fork. Okay, you may have statements before this fork. So when you get to the fork, the sequential execution is suspended, and the statements in the fork join are executed in parallel, and then the sequential execution resumes after the join once all, that's the key, once all parallel statements have completed. Okay, so if you have multiple ones in here, all of them have to complete before it continues after the join. So here's our same example. We had statements A, and once they've executed, we want to execute two other things in parallel, which were our B statements and our C statements. And then once those had both finished, then we wanted to do our D statements. So this is how you can write that using the fork join statement. So sequentially, these statements execute sequentially. However, when you get to the fork join, these execute in parallel. So now let's take a look at a real example here, and I've put in some delay values for my statements just so we can figure out how things execute in time and when they'll finish. Okay, so in this case we've started this initial block, and this initial block, this is our first statement. Then our second statement is this fork join. Okay, so these execute sequentially, this one, then the fork join. So when this one executes, it's done after 5 time units, whatever that is. So after 5 time units, this fork statement begins. Now remember, in the fork, the statements all execute in parallel. So this statement, this begin-end statement, and this statement all execute in parallel. So this statement begins where we finished here with a delay of 5. So it begins at 5, and where does it end? It's going to end at 14, the 5 plus 9. So that's where that ends in time. Now we have another block. Now we have another statement, a begin-end statement, and it's going to execute in parallel with this. So in other words, it begins at the same time this fork was entered, which was time 5. Okay, so within this block now, this begin-end, these statements are sequential. So you've got 3 statements, this one, and this fork join, where these two will execute in parallel. Okay, so where is the time going to be when this statement begins to execute, this begin-end? It starts right here at the beginning of the fork, at time 5. That's where it starts. That's where this begin-end starts. So now if it starts at 5, when's this one going to finish? It too is going to end at 14, the 5 right here where we started, plus 9, 14. Okay, this one then is going to end at 23 because these statements are sequential. Now we get to this fork join statement. Okay, so now we have these statements execute in parallel. So the first, so both of these statements right here are going to start at this time, 23. But they're both going to end at a different time. This 4 is going to end at time 27. So the 23 plus 4 is 27. The 6 is going to begin at the 23. That's where we came into the fork. So it's going to end at time 29. So when does this join end? Remember, all the statements within the fork join have to complete before we get to the end of this join. So the longest one here is the 29, so that's the one that's the time when we get to the end of this fork join. Okay, so now we've done this statement, we've done this begin-end statement, we've calculated the time for it. Now we need to calculate where this statement begins and ends. Well, it begins where this fork began, which is at time 5. So it's going to end at time 5 plus 16 is 21. Okay, so now where does this join end? Well, the join ends, of course, when all of the statements within the fork join, when all of them have completed. So this statement ends at 14. This begin end block ended at 29. And this one ended at 21. So the longest one was 29 because they all have to have completed. So therefore this join is finished at time 29. Fork joins are useful for waiting for multiple independent conditions. So one example could be a rising edge on an ACK, and we're wanting to see if that comes within a certain time frame. In this case, we're going to say, okay, I want to look and see if it, we're going to use a time scale of 1 millisecond. And if it doesn't happen in 1 millisecond, I want to print out a timeout, that I got some timeout, okay? And we're going to see, well, can we do it like this with a fork join, okay, where we wait for the ACK, and another one where we wait for a 1 millisecond timeout. Is that going to work? Well, we actually have a problem trying to do it like this. And let's look at what that problem would be. Let's say, in our first example, okay, we have a fork join here. And our first statement is this, where it's waiting for the positive edge of the ACK. Our second statement, which is the begin-end statement here, basically waits for a millisecond before writing this timeout. So let's say that the ACK never occurred. Okay? Let's say that this statement never completed. Okay? Well, we have a problem. Yeah, it'll print out after 1 millisecond, it'll print out we got a timeout, that's what we wanted. But the problem is the fork join doesn't end until all the statements have ended. So if this statement here never ends, this fork join will never end, and it's just going to sit there and repeat this timeout. So it'll always it'll report a timeout here, and it won't continue. The other case is, okay, let's say we got the ACK within 1 millisecond. So this statement completes, it's all done. And this one here, well, it's still going to wait for a millisecond and still going to report that we got a timeout. So that isn't going to work. So what we need to do is we need to name the fork join blocks and be able to disable them at a certain time. So let's look at this. The fork join blocks can be named, and the named fork block can be disabled, in which case the execution immediately resumes after the join. And the named fork block can contain local declarations, like we did before. So here you can name the fork join block, you can put in your local register declarations and your other statements. So let's see how we could use this now. Here we have our time scale of 1 millisecond. We've named this block wait for ACK, and now we've put in 2 statements basically that are going to execute in parallel. Okay, and the first one again is going to wait for the positive edge of ACK, and if that happens, it's going to disable the wait for ACK, so it'll force it out of this fork join. And here, in the other block, if the timeout occurs, then we're also going to force it out of the ACK join in case the positive edge of ACK never occurs. So the first event to occur will abort the fork join, which is what we want. So this is how you can do that. So you name the fork join and then use your disables so that the first thing that you're going to do kicks it out of there. Let's go back and look at non-blocking assignments a little bit now. Pending non-blocking assignments assigned inside a disabled block are removed by some simulators but not by others. So this is something I want to show you, and you could run across it. So here at the current time I've said r equals 0, so that goes in over here as 0. Then I've said assign a value of 1 at the current time plus 1 time unit, so that's here. And then I have a block that I've named block, a begin-end block that I've named block, and I'm assigning r a value of 2 at 2 time units from now, and then r gets assigned a value of 3 time units from now. Okay, so we've got all these assignments from the current time. Now let's say though that because remember these are non-blocking, so there's no time, we're still in the current time step, and then all of a sudden we said disable block. Well, some simulators may actually may remove this pending assignment here from this block, which was r equal 2, and some may not. So this is something you have to be aware of. So in other words, your model will execute differently on simulators that remove disable pending non-blocking assignments compared to those that don't. And at the time that I originally did this, these were some of the simulators and how they reacted to it. So you may want to check your particular simulator if you, for some reason, do this. Now we want to look at procedural continuous assigns. And there's a couple of forms of this. And one is where we use the assign and a deassign statement, and then we're going to look at the another pair that are called force and release. It's similar. We can create a temporary continuous assignment on a register, okay, and it overrides the existing assignments to a register or net. You can remove assignments by using the deassign statement. So the assign can create temporary continuous assignment on registers or concatenation of registers, and it overrides the existing assignments, and then the deassign removes the temporary assignments. Here's our syntax. Assign a target equals some expression. And then when we're done, deassign target. Okay, so this is something you should only do temporary. It's just for simulation purposes. And let's look at an example of a flip-flop with an asynchronous set and reset. So here there's a block that has always that pause edge clock. We assign the Q equal to the D. So we would call this our normal operation for the flip-flop. However, if we have a clear or a set, we're going to want to override what goes out on Q. So if we got a clear, we want to set Q to 0. Otherwise, if we get a set, we're going to set it to a 1. Otherwise, deassign Q, so it will remove the override. Okay. This is not the best way to do things, and I don't recommend doing this because if you're trying to write code that's synthesizable, some simulators might, some Verilog compilers might let you do this, others won't. Okay. So again, I don't recommend that when you do things to a particular register like Q that you use different blocks. Keep all your Q assignments in the same block. Okay, it only works on whole registers and concatenation of whole registers. You cannot include a delay or a strength, and subsequent procedural continuous assignments replace the previous one, and it doesn't add any type of driver onto the register. Now we have another pair of procedural continuous assign called force and release, and I prefer this pair myself because you can create temporary continuous assignments on both registers and nets. The other one was just registers. I may have had a statement in there that said nets or something, but the other one's just registers. This one's registers and nets. And the force overrides existing assignments, and the release removes the temporary assignment. Again, same similar type format. So let's look at how you might use these. Let's say you had an assignment statement of just assign out equals A and B and C, some simple assignment. And here we have a module, my DFF, and here's the instance name, DFF, and here's the signals that we're feeding into that instantiation. Now here we have the initial statement. So we wait in this initial statement for 50 time units. Then I'm going to use the force statement, and I'm going to override this assign statement up here. So I'm going to override it with this temporarily, from all the way from time 50 till we get up to time 100. Okay, so I'm going to force out to be equal to this, and I want to force the Q to be a 1. Okay, so now after 100 time units, I say release Q and release out, so they can go back to their normal operations. Okay, so registers continue to store the force value after release, but can then be changed by a future procedural assignment, such as at the pause edge of clock. Maybe it clocks in the new or correct value. Nets, however, return to the normal driven value when they're released. Okay, so these force and release statements are very useful in simulation or debugging, and you should only use them for a limited time period, and do not use them in your design blocks when you're going to write synthesizable code. You don't use them in that. Okay, very useful though for simulation. One useful feature is you could use them for making sure you're forcing certain registers in your design to a known value on reset for your simulation. So in Lab 6.2, I want you to become familiar with disabling blocks and to learn how to use the fork join statement. I want to talk about min, tip, max delays. We've talked about delays before, but any delay specification may be specified as a minimum, typical, and maximum value triplet. Okay, we use the pound statement for delays, and we're going to take a let's look at the syntax here. Before we had just a pound and then some delay value. Now you can have a minimum expression, colon, a typical expression, colon, max expression. Now let's look at how we actually use these. Here we have a buff, and we have the pound statement for delay. And instead of having just a simple rise value and a simple fall value that we talked about before, now we're going to use the min, tip, max delays. So these are the values that we'll be using for rise, and these are the ones that we'll be using for fall. Here we have some code, and we've actually, in the pound delay, we've specified a min, tip, and max. This is another format you might use. But here you can also make some calculations in here if you need to. These would be constants that would be declared as parameters typically. So they don't have to be just a constant number in here. You can actually do some things like this. Here's another example where I said 2 times scale. And this is just a simple delay, except for the fact that we declared a parameter scale and we gave it min, tip, max. So now this is 2 times each of these min, tip, max. So parameters can have min, tip, max values. So now how do we use these? Well, the compiler, your Verilog compiler, picks one value at compile time. Okay, either the minimum, the typical, or the maximum. Okay, so simulation will run only just one of the following, either all minimum, all typical, or all maximum delays. And to select the delay that you're going to use, which mode you're going to use, you would use the following command line option, like plus min delays, plus tip delays, or plus max delays. So it's just one of these that it's going to use at runtime. It's going to do it at compile time, but just one of them. Oops. So in Lab 6.3, I want you to learn how to invoke a simulation with min, typical, or max delays, and learn that simulation results can change by using different delay modes. And that's the end of our class for today.